guess so. All right, so my name is Chris Berry. I'm here to discuss and ignite compute grid in the cloud. And this is a sort of in the trenches talk. A lot of echo. So let's just get started. So the application that we're going to talk about today is called internally Akira, and it's in case y'all don't know what we do at HomeAway, we're a company that does vacation rentals. VRBO is one of our companies, et cetera. We own a lot of companies. And the application we're going to talk about is called Akira, and it's the rates engine for HomeAway. And it's basically how we compute quotes based on cached rate data. So if you come onto HomeAway and you want to know the price of some rental you want in Paris, you would go through this engine to get that data. It's a high volume, low latency application, at least for us, and it computes about 12 billion quotes a day today at about a 40 millisecond P95. Those quotes are computed in batches of approximately 200. Most of our traffic comes from the search engine. And so we see about 2,300 batches a second. And there's about a half a terabyte of rate data. And the job that we're going to do in this talk today is to take this old school terrestrial deployment of Akira up into the cloud. And we're going to simplify whatever we can in the process, and we're going to modernize the stack while we're at it. And of course, we don't want to break anything while we're doing it because it's real code. So let's take a look at what the old school Akira looks like. And really, for the purposes of this application, we don't have to know much about it. We'll never talk really about how it works internally because it doesn't really matter in this discussion much. But a request comes in to a smart Akira client. It goes off to a load balancer, in our case, NetScaler. That's sent down to a VIP. The VIP then translates it to a set of nodes called aggregators. The aggregators, you can really think of them as map producers. They then take that request, figure out what node below it, which are called quoters, actually have the data in order to do that job. They do their work, passes it back up, the aggregator reduces it or puts it back together, sends the request back out to the client. It is of interest in this discussion really is that these aggregators know which quoters to talk to, and it's a bespoke or sort of a hand-rolled, sharded system sitting on top of a hand-rolled distributed hash map. And this was all built, I don't know, 7 years ago or something. And so it's down inside these quoters is a lot of code, hundreds of thousands of lines of code, and it's complex. Any code that's this old has, grown to be a beast. So I'm sure those of you who paid attention could see why this would be complicated to take this terrestrial app up into the cloud. First and foremost, the stuff's statically bound together. You've got a statically bound VIP, and then underneath that, you've got a statically bound set of quoters that know what shards or what group of data they're working on. And of course, anything that's statically bound like that doesn't work well in the cloud where things come and go. And of course, the other bit is that we have bespoke MapReduce, bespoke sharding, we have a hand-rolled distributed hash map. All of that is complicated in the cloud. Because we've hand-rolled this, we tend to have pretty large heaps because we don't reshard that often. So, of course, large heaps in Java mean a lot of garbage collection, which means a lot of trouble. It's complex code to maintain, and we want to modernize the stack. And unfortunately, some parts of it were written in .NET, and which, let's just say, is difficult in Docker, just due to licensing issues, et cetera. And we're a Linux shop, so all in all, we want to, we need something new. So, of course, the first thing you're going to ask, I was dropped into this project, and the first thing you're going to ask is the same thing I asked, which is, why don't we just use memcached or Redis or something else to pull the data up from and get rid of all of this bespoke stuff we built? Well, unfortunately, those pesky laws of physics get in the way, and the rate data itself is about 1/4 of a megabyte per unit. We compute them in batches of 200 over a gigabyte network. That's about a half a second right there off the top. Of course, you can do that in parallel, et cetera, but you're never going to get away from the time it takes to bring that data to you. And that's before you ever start doing any computing, and this thing takes a lot of CPU. So that's, how did we solve the problem? Well, that's why we're all here. It's really because of, for in-memory computing, how we solved it. We chose to use the Apache Ignite compute grid to do this, and really because of the co-location of compute and data, and the distributed caches with Affinity, and the fact that it has a very simple MapReduce built into it. So it met our needs beautifully. And so how did we go about doing it? Well, I think we should, I'm going to sort of as a from the trenches thing, let's start at the beginning at how we accomplished this. Well, first of all, we already have a very well-written, well-tested code base, and we don't want to poke the bear. We want to perturb things as little as we possibly can, and on top of that, we had to allow for concurrent work to happen, because feature work continues constantly on this code base. There's a team of guys working on it, and they can't be disturbed, really. Luckily, Ignite is almost a drop-in replacement in our case, because we have a hash map and an Ignite cache basically have the same interface. So how exactly did all of that work? Well, the first thing we did was we dropped into that code and we added extensibility where there wasn't any before, which really means just adding interfaces where we needed them. And primarily so we could swap out the hash map, the old bespoke distributed hash map for Ignite caches, et cetera. And then we took all of that existing code that used to wrap up into a war and extracted it out as a jar and left behind all the bits we didn't want anymore, which was all the old school stuff like Jersey 1 and things that, and then all the bespoke parts we didn't want anymore. Left that behind, grabbed it out as a jar, dropped that into a more modern Drop Wizard project, and then Drop Wizard always works as executable jars. Took those artifacts, pushed them up into Maven, and then I built a reusable Jenkins job that allows you to wrap Drop Wizard apps, because they all work basically the same way. And so I just built a reusable Jenkins job that would pulls that executable jar back out of Maven, wraps it up with all the necessary configuration, wraps that up with some reusable control scripts written in Bash, so the thing is basically generic with some 12-factor stuff applied to it, rolls all that into a Docker image, and it's built on a layers of Docker images, because I'm sure all of you that use Docker are the same as us, that security has to bless your images. So we have blessed images of Ubuntu, we have blessed images of Java 8, and then there's a blessed image of this reusable bit that sits on top of it that's based on Docker on build and build args, which is how you parameterize Docker. And then on top of that is a very little bit that gets taken out, dropped in with the necessary bits, and then we drop out an image for any one of the, for basically any service we built, but in particular for Akira, what we're talking about today, and drops that into a Docker repo. So now that we have a Docker image, we have to deploy it up into AWS, and how that works is we have to drop a little bit into how we do that at HomeAway. At HomeAway, we've built a system we call Multipaths, which is basically our version of platform as a service. It lays on top of Mesos Marathon that runs the whole thing. For the orchestration of the containers all run inside of Docker, of course. It all lays down on a base infrastructure that we lay down with Terraform to create all the AMIs that we drop into AWS. And then we have a base infrastructure that we lay down on every single host that we deploy. And that consists of console for service discovery, container pilot for doing basically to make service registration easier. And also, by the way, it provides a way to launch Java apps so that they get launched properly and get signaled properly. We use Splunk for log forwarding. We use Datadog for metrics, but we had to hack the Datadog agent so that it understood console. We use Linkerd sticks, which is something HomeAway is open sourcing. A DNS mask to create a service mesh, which is basically like essentially a DNS masking of all the services that live in the region. And then we use Vault for secrets. The secrets is a really big issue, of course, in all of AWS or all of the cloud, but we won't go into it. But Vault is the basis of what we do, but it's far more complex than that. So putting all this together, we get a base infrastructure that looks like this. You basically have a host that gets laid down, and it's managed by the Mesos master. But on every host, there's a Mesos slave that's an agent that's run by Mesos, that then runs the Docker engine. That Docker engine runs all the Docker images that it's supposed to in that particular host that it's told to run. And then that particular Docker image, there's several agents that get laid down in the infrastructure that you can depend on to be there as an application developer. They include, as I said, the Datadog agent, which is constantly polling your application for metrics. The console agent, and the nice thing about the console agent, and actually all of these agents, is they're all running locally. So there's no off-box hit when you need to go off to get to talk to them. So you run a console agent, and so every image when it starts up, like I said, Container Pilot is registering that service with console, and then the image itself can then talk to console on local port 8500 and find out what's running on the box, and also what's running out in that region. Linkerd is, as I said, that's in order to actually know about the mesh of services that are actually running. And then, of course, the Splunk forwarder, because if you can't see your logs, you're pretty much out of luck. So what we do is we write logs to a specific location. Those logs are then volumed out to a very specific location. The Splunk forwarder knows where to get them. So there's a bit of convention over configuration, et cetera, that sort of helps this whole system hold together so that the developers, the applications, and all the services primarily know how to find each other, because in the end, when you're dealing with the cloud and you're dealing with the microservices world, you'll have thousands of services, and if they can't find each other effectively and efficiently, then you're pretty much screwed. So the linkerd bit is what really enables that, because you can simply go to the local, that's all local host hopped. And then once you're there, that's a software load balancer that's keeping you and pointing you directly to the cluster. And we'll see how that works. But so now let's drop Akira into that same infrastructure. We're out now, we see an AWS region there. And it all works basically the same way as it worked before. You have on some other host, you've got a client, he makes a call into his linkerd. That linkerd knows where all the other services are, knows where our particular Akira nodes are in the Ignite cluster, calls one of them. It does the same sort of map reduce we saw before, but it does it inside of Ignite. It maps out, says, okay, which nodes have this bit of data, sends it off to the nodes in the ring, gets down to our node there that we're showing. And the only bit we didn't discuss previously is really that we also run on every region's running mirror makers for Kafka, and that is how we seed our caches. And that works really beautifully, because what we do is when a deployment starts up, it's given a deployment identifier, and that deployment identifier allows all of the nodes in the ring to identify each other uniquely. So you can run lots of clusters in the same region without them stepping on each other, because they're all self-aware. And they also can join a Kafka consumer group with that identifier, which keeps them from stepping on each other, and they can all begin reading from zero and fill their caches. And because that's all done in parallel, because it's done with consumer groups, you can load the caches extremely quickly. And more importantly, it provides resiliency to the system, because I can axe any node at any time, and some other node's just going to pick up those partitions out of Kafka. So I think for what we're doing here, since this is an in the trenches thing, you want me to, let's get specific on what we had to do actually with Ignite to make all this work, and how we tied the whole room together. The most important thing we got out of Ignite was its compute grid and the whole cache affinity thing. And for computation, the computation bit, well, that's easy, because we simply deploy a cluster, and we've turned off all that stuff that allows the code to move around the system. We simply assure that we've deployed all the same code on every node. So that's simple. We run a whole series of caches that are all partitioned in the parlance of Ignite. And those partitioned caches have to end up on the same boxes, right? Otherwise, all of this is moot. So in order to do that, we use the same key set across all the caches, and the affinity functions inside of Ignite ensure that for any given key, all the caches that on every box will contain that key. So once you end up on one box with one of those keys, all the caches from that box will be there for that particular key. So that means that all the data is co-located that you need. So we rely on that heavily for this to work in our system. And we use a flag that you can set in Ignite called setLocal that ensures that if the data is not local, we're going to throw an exception out. So it works. The other thing we use pretty heavily out of Ignite is the resiliency that's built into it. We use, today at least, we use 3 backups and 1 primary. And so we have a total of 2 terabytes of data spread out there. And we typically do that on about 20 nodes today, 20 AWS nodes to run this system. And this is nice because it really allows us to withstand the ephemeral nature of the cloud, because nodes do come and go. And you can see from the graphs on the side there that we do lose nodes, and the caches below self-heal. And in fact, it really isn't what it looks like there. It looks like you've lost data for a little while, but really that's because that graph is of the primary, but the backups have actually taken up. And if you really looked at the true responses seen from the client side, it doesn't see these incidences at all. So what did we have to do specifically sort of to make all of this run up in the cloud? Well, the first thing we did was, as I told you, we use Console for discovery. So we had to build a Console IP finder. Ignite ships with a AWS IP finder that keeps the data out in S3, but it wasn't very secure. So we wrote our own, and since we use Console anyway, that's what we wrote. And it works like this. Basically, Docker, as it's firing up, it fires up Container Pilot. Container Pilot, the first thing it does is it registers your service. It pulls the JSON from a templatized JSON and then says, hey, I'm going to register a service named Ignite Disco, the discovery port for Ignite. And then of course, it knows what address it is and what port it is because it's registering itself. And more importantly, it sets a tag, and that tag says, I am ID with this deployment ID. So in this case, It sends that off to Console. Console sticks it in its service registry. And then the next thing that Container Pilot does is it launches your app. Like I said, it basically does a fork exec on your app. And then it launches Akira, our app, which launches Ignite. And then Ignite does what all these clustered systems do. It goes off to find some seed nodes. And we then go off to Console and say, Console, tell me about all of the Ignite Disco nodes that you know about that are passing their health checks and are tagged with this ID of that we just stuck in there. And it looks in its registry, builds that list, sends them back to us, and then we decompose it and send it off to Ignite, and we get our list of seeds. The next thing we had to build to make all this thing, to make the room fit together really was, we had to build an expected grid size monitor because we prime these caches right, and so we need to know when the thing's ready to be used. And none of this is built into Ignite. So we built this expected grid size monitor so we know when we're whole. And so how that works is we have Akira, and at some point when it's starting up, it asks this thing that's called the Ministry of Truth, which is something that we wrote that is a part of that Multipaths thing I talked to you about. Because in all of these systems, there's two concepts of truth. There's the truth you intend, like we intend to run 20 nodes, and then there's the real truth, how many nodes are really running, and that they're not always the same. In fact, they're definitely not always the same. So we have to ask the Ministry of Truth, how many nodes did you intend to be running here? And so it says 20. And then at some point along the way, we start up this expected grid size monitor and say, hey, you should be looking for 20 nodes. It goes in, tells the Ignite grid to start listening for grid events. Those grid events come in, we count them up, and when we get to 20, we fire two things. We fire a grid, we write a grid started flag into a shared data space, which is just a cache since we're running shared memory anyway. So we write into there that's several pieces of data, but one of them in this case is the grid started flag, and then we fire a grid started off to the Akira, so it can then wake up and start the Kafka listeners. As I said, we have an administrative data cache, and the other thing we had to do once we had that cache of things, we needed to be able to look at it. Because, for example, when a node starts up, I mean, you know, if the thing's running for a week or so, or 2 weeks, it only started once, but nodes come and go. So it needs to be able to go and look and see what, it doesn't, I mean, when the node starts, it doesn't know its own state, right? So it has to go determine the state of the grid. So it goes off to the admin data cache and pulls that data in. But Ignite has an interesting thing in it called a continuous query. And so we start one of those to watch a particular row in a particular cache. And that's basically the code for it there. But the only thing about these that you have to be sort of careful about is that they're not free, so you need to turn them on and turn them off. So basically, we start them when we need them, turn them off as soon as we possibly can after we've pulled the data out on any given node. So that you would only want to really use them for something like, in my humble opinion, for something like a administrative cache like this, which has very, very low writes to it. And the last thing we had to write that was sort of specific to make all this work, that wasn't just sort of canned Ignite stuff, is we had to write an availability zone, an AZ-aware backup filter. So like I said, we keep 3 primaries and one primary and 3 backups, and we need to keep we need to be able to lose an entire AZ. That's kind of what you have to do up in the cloud. So, and we keep 2 AZs across every region at the moment. So we want to be able to lose one completely. And of course, the grid itself spans the whole region and spans the AZs. So in order to make it so we can lose an entire AZ, we've written this little AZ-aware backup filter that just sort of knows whether the node that you're looking at is in which AZ and keeps the primaries and backups balanced. And we do that really by using a thing that's built inside of Ignite called the consistent node ID. And what we do when we build a consistent node ID, we encode a ton of information into that consistent node ID so that when it comes back to us, we can decode it and use it for all kinds of purposes, because that's really the only piece of information you're going to get back from them is that little piece of information. So you've got to encode your own information in it. By the way, we also encode both the IPs and the ports and a lot of other information, because it's really how you decode these or debug these systems. And finally, about debugging, we've built in request scoped tracing into the system as well. We already had request scope tracing in general. We've had it for quite a while. But of course, we had to adapt it for the compute grid because, and then we modernized it at the same time for Drop Wizard. And so what we do is we register a Jersey container filter and a logback MDC filter. And so when a request comes in, you can add a specific header to that request. So when somebody's trying to debug something, because clearly in a system that does 12 billion quotes a day, I can't turn on any debugging, right? It's completely, you'd blow your logs out. So we basically need to be able to turn on trace level debugging for a transaction. So you send in a request header, an X header, it says turn on tracing, and then it toggles on trace level logging using this hacked MDC filter. It turns on trace logging and then passes through the GUID that got sent in originally or got tagged for that request, depending on how it worked, because the GUID will pass around, and it will then get set into the MDC, and then of course it ends up in your logging through standard MDC logging. So, and that's really quite useful because people have to debug these quoting algorithms a lot, and they need to be able to figure out to turn on the very, very detailed logging. So that's really, in a nutshell, all the things we had to do very specifically to get this thing to work in Ignite, beyond, of course, the regular work of just yanking out the old distributed hash map and putting in all the new stuff. So how's that going for us? Well, you saw originally we said that the performance when we started was basically 2,300 batches a second at 40 millisecond P95. Right now we're sitting, by the way, we're going into production next month, but we're going to dribble it into production. We'll be fully in production by in January. But that has really more to do with business concerns. But today we're sitting at about, as you can see, the P95 there is about 70 milliseconds. So we have a ways to go, but we're running on M4 4XLs right now, and we're pretty convinced when we move to R4s, 4XLs, that we're going to get significant improvement in that number. My bet is it'll have it, but we'll see. But we have it. It's not that simple for us to just change on a dime and start running on the R4s, even though it sounds like it might be. So that's happened. That's in process at the moment. But so that's where we are perf-wise, and that's really it. I'm gonna take any questions, and of course the obligatory, we're hiring. So if anybody is interested, bring me a card. So that's it. Any questions? Yeah. Go ahead. No, you right there. Sorry.
It sounds like you're not running across any regions for your clusters, so you just keep your region within, or excuse me, your cluster within a region. But did you try that and see if there were any challenges? Or
no, we didn't try because we don't really need to, so we didn't complicate it. The question was, why are we running cross-region? And in our case, the real cross-region bit there was the Kafka bit, because that's where the real data is coming up from. So we basically actually use the other regions to keep, we're running the same thing in multiple regions. And so if there's trouble, we can flip to the other region. Yes, sir.
Yes, you mentioned that you implemented your own discovery kind of discovery node. So although I think Ignite discovery as well, so that S3. So I'm just curious to know, like you mentioned that it's not secure because we've been using Ignite discovery, and so far I think our experience is fine. But I'm just curious to know, like, I guess what was the key reason that you decided to implement your own instead of leveraging the Ignite discovery?
Well, the username and password was in plain text, so that's why. And the way you had to set it, the way you had to set the whole thing up was, you had to put the username and password somewhere. So, and we didn't feel like fixing all of that, so we simply we already used this other discovery mechanism, so we went there. They're really not that dissimilar. Essentially you just have to keep a list of nodes that are running. Since we already have to register with console, because that's what ties the whole system together, we already had the information there, so And we didn't have to have any username and password, or we didn't have to go off to S3 or anything else. So we stayed on box because that call to console is all local. We don't have to go call S3 for any information, et cetera.
Okay,
So.
the follow-up question, I think that you mentioned also the monitoring tool as soon as one of the nodes goes down, right? Did you implement your own monitoring tool that actually detects as soon as it goes down and then you bring up another one?
To monitor that?
Like, yeah, I think you mentioned that, like you have, let's say you have 20 nodes, and as soon as one of the nodes goes down, then you have to bring up the 20th node, for example.
Oh, the question is, how are we managing essentially when a node dies, another one starts. That's all Mesos Marathon. That's all built on that system. That's really what it does for you. That and auto scaling, et cetera. So we don't maintain any of that. Now, and Ignite itself understands when nodes come and go, so it's already easy there. Yes, sir.
Did you see any performance difference while running Ignite as a container as you're running with Mesos Marathon, or just bare metal?
I wish I could answer you truthfully, but I've never run it outside of a container. So, except on my laptop, right? So, I don't know the answer to that. We have no way. We don't really run in AWS except in containers. So, I wouldn't really know the answer. But everything does stay pretty local. The way that this, Ignite itself is talking directly to the other IP and port, right? It's not going even through a load balancer at all. So it's about and internally I don't see any real difference in the container, but I will say that AWS, the boxes themselves is really critical. I mean, if you use a crummy box up there and you move up through it's really Ignite is really about networking, and if you use let's just put it this way, they definitely throttle you. So if you are using a lower level AWS box, you are going to get lower level performance. And if you use any T2s or anything, they throttle you, and the real problem with Ignite and with these compute grids is, and I'm hopefully going to talk to someone here today that can enlighten me, but the problem is it's mapped, right? It maps this whole thing out, and if you get one node that has a noisy neighbor and starts getting poor responses, actually, like here, you see the compute tasks and the compute jobs and stuff. If you see in our case, the compute job isn't really, it is there. Like it's normally running about 4 milliseconds. If you see ones that just start running at 8 milliseconds, it will have the means, the full means. And you'll literally start seeing half the response times from one node out of 20. So it's very sensitive, and it doesn't throttle internally and understand, well, there's a slow one, I'm not going to send it any, because that data is already on 4 boxes, right? So it should be able to send it to one of 4 that's not so slow, but it doesn't do any of that kind of work. So you kind of have to watch that sort of thing yourself, and if you start seeing some nodes because that's the real problem in AWS is you might manage your own, you might be able to manage yourself noisy neighbors, but in AWS, the host you're on may have a noisy neighbor, and you can be scratching your head and saying and going, I have no idea why this is exactly the same stuff here, why this one box is performing so horribly. And now the beautiful thing in AWS is you can just assassinate that node and start another one, but that requires processes to do that, and so. Yes, sir.
So for colocate processing, did you use
We used the, I think, it's hard for me to say. We just used basically the code that was written was a hash map, right? And then it already had a little layer above it. And so I basically just am using, it's real simple, just gets and puts and put alls, et cetera. So I'm not sure if that's the part of JCache or just Ignite, honestly. Because it's just basically hash map stuff.
It's a combination of Affinity and the distribution.
Yeah, the Affinity part definitely is like you have to call the Affinity part out when you build it.
It only supports the processing, so it will be lost entry while processing. Ignite does support the normal. So my question was basically, if you had to log the entry to start processing, what would be the performance gains?
I can't really hear you, I'm sorry.
No, so if you have to log the key to start processing, right? And what would be the performance gain for your computer? So is that, if you notice any, if you use JCache API, it logs the key.
Oh, yeah, we're definitely trying not to lock anything, because it's very, very read centric. It gets very, very little writes, and we don't really care. Even though JCache itself, we use the atomic writes, or it is atomic, but it could be eventually consistent for all we care. Really, we're only about doing it as fast as we possibly can. And literally, like I said, if they, when you go from 4 milliseconds to 8 milliseconds, those means will double. So we have it's very, very sensitive, and it pegs out the CPUs. So we're not too concerned about whether the data is locked at all. In fact, we don't want it locked, or we prefer not to pay any overhead for locking. Yes, sir.
How does the scale of your infrastructure compare between the terrestrial solution and the AWS solution?
What's the question?
Your infrastructure.
What's the difference between it?
What's the difference?
I'd say it's probably worked out in the wash, honestly. I mean, because we had all these aggregators, and then we had all these quoters. Now it's all in one system. So I'd say it's probably in the wash. It's probably like 20 nodes in 20 and 20. We're still scaling it a bit because like I said, we're not quite in production yet. So we're still scaling it up and down to get the performance it's really more about resiliency than it is about that. If you didn't lose nodes all the time and you didn't have to be so careful, we could do it on a lot less nodes. But now because of the real fact that you can lose nodes, and you want it not to stumble, that's really, so that, like 3 backups is a lot of backups, really. And we usually run Elasticsearch with less backups than that, et cetera. But it's a fair number of backups, but it's really because of AZs and all of that stuff, right? So it has more to do with that, really. But I think that the cloud is very, there are issues, because of the ephemeral nature that you probably have to run more boxes. I will say this, that I think that a lot of people act like things come and go constantly in the cloud, and I think the reality of that is very different from what people say. We see really from AWS itself and EC2, we see about, I would say, a 1 to 5% death rate across all the all the hosts we run, which, is a lot, I guess, but it's a lot less than what people run around the internet and scream and wave their hands about. The real death rate comes from maintenance, because people have, this stuff you're seeing, that infrastructure we lay down, it has to be upgraded. Right? People have new versions of things, security fixes, whatever, and that means you got to sweep through that whole infrastructure and do maintenance on it. And that's really where your death rate comes from, as far as I can tell. I mean, we have a way higher death rate, let's just say, from maintenance than we do from AWS itself. Though I think people like to say that AWS, that when you're in the cloud, you're going to lose boxes all the time, et cetera. But in my experience, that's not real. I think that's more Chicken Little than truth. Yes, sir.
Yeah. So aside from having 3 backups, can you describe kind of at a high level, like some important decisions you guys made to avoid performance impacts when losing a node?
We have, the only thing that's really a problem right now, and again, I hope to talk to the Ignite guys while I'm here, is that we've had to kick the timeouts up way higher than are sane, really. We have timeouts of like 45 seconds for things internal, because AWS does burp at times, and also there seems to be a fair amount of it can be slow on the uptake, like when a node drops and comes back, et cetera, and you don't want things killed too quickly, but you would like it to respond pretty quickly to a death, but it may not really be dead. It may just be not talking at the moment. So that's probably the worst thing, is that the timeouts have to be too high, in my opinion. But other than that, it pretty much handles itself in that nature. We haven't had to do a lot of stuff except add backups and like I said, the Affinity filters and things to try to keep the backups where we want them. And it does a pretty dang good job up to a point. But when it loses, it's kind of a double-edged sword. If you have 20, like when you have 20 nodes, and all those backups, when it's rebalancing, things take even longer, and you do take some performance hits during that, but we're sort of saved in some ways, because our software load balancer is pretty like when you have 20, we have 20 in a ring, and when it pretty quickly says, I'm getting 500s there, and takes them out of the software rotation. So that happens really quickly. So we see, even in really bad outages, like that one I showed you where we lost an entire AZ, we only see about 0.003% errors, which is not great, but it's certainly not horrid. Because what you're basically seeing machines that you got 20 boxes running, and you've kill minus 9, 10 of them. They're gone. Well, there are in-flight transactions. Stuff's happening, right? So you're going to see some 500s coming back, but the software load balancer pretty quickly adjusts and puts the load on all of the ones that are healthy. So that is also a big saving grace in this whole thing. I will say that bit of the infrastructure that you saw, that is probably the most inspired bit, is the linker D bit. And actually a friend of mine is here. I used to work at E-Trade for a long time, and a buddy of mine from E-Trade is here. And we were just talking about this, and that bit is what really does tie the whole room together, because it provides the software load balancer but it's a middleman and so every transaction's going to it. It's all on box, so it's as fast as it could possibly be. But because they're all going through there, you've got a middleman all of a sudden that you didn't have before, which provides us a way to slip in things like tracing, real tracing, like Zipkin type stuff. So it provides all these other benefits that you kind of don't think about when you first build it out, and all you're getting is your service mesh back. Because, the client itself is able to say, to connect to just, in our case, it's a DNS, it's just service.local. And so you would be like, if I'm going to call foo, I'm going to call foo.service.local, and that's what's in my config. So my config never has to change ever. So, and that's beautiful for keeping all the clients, not having to recode stuff all the time, right? But it also means that they're going to jump out to that linker D, and so you can basically do all your tracing at that level. So it's a pretty beautiful thing. And you get it, and it's a pretty dang good load balancer. I think I'm done, right? You want me to leave? Okay. And you can talk to me afterwards if anyone has any other questions. Thanks.